Okay, so welcome everyone again. The next talk is by Manas Kulkarni from ICTS, and he'll talk about collective behavior of a family of power law models. Manas.
Hello. Yeah. Thanks, Abhishek. So first of all, I would like to thank all the organizers for giving me the opportunity to present some of our recent works in this very nice discussion meeting. So today I'm going to speak about collective behavior of a family of power law models. So this work has been done, several parts of this work has been done with several collaborators, Saikat and Jitendra, who are PhD students at ICTS, Sana, who was a visiting student at ICTS, and Abhishek and Anupam, faculty colleagues at ICTS, Satya Gregory from Paris, David Mukamil from Weizmann, and Avanish, who was at ICTS visiting, and Dipankar, who is a postdoc at ICTS. So most of the things I'm going to speak is available in these references. So the contents of my talk are as follows. So I'm going to start with some definitions, statements, and questions. And then after that, I will move to background and motivation. And then I'm going to discuss some results for large N theory and densities. So the focus is going to be power law models. And I'm going to discuss what happens when you put barriers, in these power law models. I'll discuss gap statistics and also some time dynamics, some very preliminary work on time dynamics. So let me just start with some definitions. So what we are interested in is a classical system of n particles on a, let's say, on a straight line, where everything is basically, everything is coupled, interacting with every other particle. So this is what we call all-to-all coupling. And on top of it, these particles are confined in some external trap. I'll take this opportunity to thank Anupam for providing many of these, a lot of these figures and material for these slides. So this is the energy. So the energy is basically given by, there's some external potential, and then there's some interaction part. Okay, and the external potential is such that at x going to infinity, you basically the external potential also goes to infinity. So it's a bounded external trap, and the interaction potential is such that it's pairwise interaction, and it has this property that for small arguments it just goes as 1 over r power k. Okay, so where k is basically the exponent of the power law interaction. So the value of k characterizes, so to say, the strength of the pairwise interaction, and sign k basically ensures that these are always repulsive. Okay, so k is what is supposed to be, we have to pay special attention to k. And external traps, we can consider several ones, but I'll be focusing mostly on x square. So this is basically the general model. So you have particles which are repelling each other by some power law interaction, so they cannot come too close to each other. At the same time, they cannot fly apart because they have this confining potential. Okay, so let me just say a few things. So basically what happens is that the external potential tries to confine the particles near the center of the trap, and the repulsive interaction tries to push them apart. So one can ask this question: what is the configuration of the particles which minimizes the above energy function? So that is one of the first questions that one could ask. And then what is the corresponding macroscopic density in the large N limit? So something like this, you can naively imagine that if you want to think of density of the particles, probably it will be like some dome, right? Because You have excess particles near the center, and then they are less and less particles. So at least for reasonable values of K, you would expect some dome-like density profile. But question is, can we write exact analytical solutions and so on and so forth? If you have temperature, basically you can write down a equilibrium joint property density function, and then you also have entropy playing a role. And then you can ask, what is this quantity? So what is the thermal average of empirical density? So you have these microscopic particles, n particles, and you're asking what is their density profile? How does the density profile look? So this is one of the questions that one could ask. So let me I'll become more concrete slowly. So let us again go to slightly specific case where the external potential is x square. So you have this harmonic trap, and the interaction is exactly this. So let us so the interaction is 1 over xi minus xj power k. Okay, so please stop me if there are any questions. And basically this model is well defined. So let me draw some axes here. So this model is well defined. So let this be the k line. This is the k line. So the model is well defined above k equal to -2. Below k equal to -2, it is unstable. So you have -2, -1, 0, 1, 2, and so on up to infinity. So the model is well defined throughout -2 to infinity. So now let us see why are we interested in this family of models. Notice that this is a large family of models. As I will try to argue, there are some very specific well-known examples that I'm sure many of you are familiar with. So first example is k equal to -1. This is called 1D one-component plasma. It's negatively charged particles with pairwise Coulomb interaction, which is linear in 1D. So this is the energy for the 1D one-component plasma. So notice that here the balance between external trap and the interaction is delicate enough such that you actually get uniform density. So this is the density profile. So the particles just get equally spaced because the repulsive interaction balances the external trap, and it just forms a uniform gas. Okay, so this is a very well-known example, and a lot of work has been done. Several of people in the from this discussion meeting have also worked in this model. So now, so let us again I hope everyone is clear with this model that we are considering. If there's any doubt, please let me know. Now the next limit is, so we discussed k equal to -1. So here I'm just trying to motivate why we are interested in this arbitrary k model, which also goes by the name of Reed's gas in an external harmonic trap. So the next limit, probably many of you are familiar, which is the k going to 0 limit. Of course, when you take k going to 0, you have to be slightly careful. You should think of k going to 0 and j times k being some order 1 constant. So if you take this careful limit, you'll get the Dysons log gas. So this is a log gas, and there's a logarithmic repulsion, and there's an external trap. So this is a very well-known model. The zeros of this model are known to be the minima are known to be located at zeros of Hermite polynomial. This model is related to non-interacting trap fermions. It has deep connections with random matrix theory. It has relations to KPZ universality class. And here the density, the resulting density profile, it takes the shape of a dome, and this dome is basically exactly a semicircle. Okay, so this is one of the example, k going to 0. Of course, one very nice example is the k equal to 2, which is the Calorimeter system. So this is the Calorimeter-like interaction with a harmonic trap, And this has been discussed already in Veer's talk, and a lot of interesting things about this model have also been discussed in this discussion meeting. And here also, interestingly, the density profile is a semicircle, and the model is integrable in external confining potentials up to quartic polynomials, and it appears in various branches of physics. So I've given three examples which are, so to say, very famous examples. And one can ask, what happens to these densities for other values of K, and what is the large N field theory of these models? So can I go from here to some representation in terms of collective densities? And then when I go there, I can do saddle point and minimization, and I can evaluate density profiles and so on. Okay, so this is the this thing. So now the list doesn't stop here. I mean, there are a lot of relevant limits. You have dipolar gas, charge-induced dipole interactions, and then if you go to K, going to infinity, you actually reach the limit of hard rods. So throughout the K line, you have a lot of relevant models as special cases. So one more thing I want to say is that harmonic trap is quite ubiquitous in cold atomic systems. So that is one good thing about this model that we are considering. And there are a lot of techniques for past many years in absorption imaging, where you can image the density of particles with very high accuracy, and you can also probe the dynamics. So what happens if you start with some non-equilibrium initial condition and probe and study the dynamics? And also there is a lot of experimental techniques to resolve at a level of single particle, single atom. So not only densities, in principle, you could probe even very microscopic quantity of interest, such as particle fluctuations and so on and so forth. So these are still examples where I'm trying to motivate why we are interested in this model, which is the Reeves gas in harmonic trap. So here is another example in cold trapped ions. So this is an experiment where you can approximately think of it as a K going to one case with external trap. And in ionic experiments, you can actually realize a range of K values in principle. And these dots here represent the locations of ions. So you can see that some of these dots are close to each other, and as you go towards the edge, they are a little bit far spaced. So you can imagine that if I build a density out of this, it would look something like this. If I build a density rho of x versus x, it will look something like this. But now the question is, what is the exact form of these densities? And what is the large N field theory for these problems? Okay, so now so we will so here is another slide just to motivate. So in principle, if you know some collective theory, and if you have suitable Poisson brackets, you can talk about some equations of motion and see how density profiles evolve. This is a very old experiment where we had seen a very good agreement between theory and experiment, and it very indirectly corresponds to K equal to 2/3 case of our system. But this is just to motivate. But I'll come back to time dynamics later. Okay, so I hope everyone is clear that we are interested at this moment in features of this model. Okay, so now let me go directly to the results. So here are some results. So and I'll try to explain few aspects of the results. So by and large, so basically, just to recap, so this is basically the regime of K which is stable. If K is less than -2, the model is just unstable. So we are going to talk about this regime, so it turns out that you can divide this problem into two regimes. One is K greater than 1, and one is K between -2 and 1. And there are two quantities which are sort of important here. One is how does the size of the system scale with number of particles. So how does the size of the system scale with number of particles, and that exponent we will call alpha K. And another question is how does the density behave at the edges, right? That is given by gamma K. Okay, so here is a plot of alpha K versus K, and here's a plot of gamma K versus K, and we see that there is interesting non-monotonic behavior, and these are the precise values you can compute. So I'm not told how to compute this, but I will sort of sketch it, and this is precisely the expression for the densities. So you see that this is basically approximately it contains all kinds of domes, right? So 1 minus y square power gamma K. So just some familiar example. If you go to the log gas case, if you go to log gas, then you go here, that corresponds to K going to 0, then alpha K is equal to half and gamma K is equal to half. So if you plug it here, you'll get something like 1/4 minus y square and power half, which is square root. So you'll get the semicircle back. So basically for the entire range of K, you can compute these densities. So here is one of the main results. So this is K equal to 4, K equal to 2, K equal to 1, and it goes on. You can approximately think of three regimes here. One is short range interactions. So when K is greater than 1, what happens is that, of course, the system is a power law model with all-to-all coupling, but the effective field theory becomes local. So there's a short range case where you can describe it by effective local field theory. Then there's a regime where it's still a non-local field theory, but the density is still takes shapes of domes. So the density still takes shape of a dome. And then there is a very interesting regime which is strongly long-range interaction, where the densities actually take a U shape. So let me just highlight this part. So if K is minus 1.5, this is how the density looks. So it is so repulsive that particles essentially want to go out to the edges, but of course they cannot keep on going because there is a trap. So particles actually start accumulating here. Okay, and this is the one component plasma where you get flat density profile. Okay, so we can compute. We have exact results at large n for these density profiles, and these are verified against Monte Carlo numerics, and there is very good agreement. So that is basically the one result of these densities. How these densities, what shape they take for different values of K.
Manas, can I ask a question?
Sure.
Yeah. So for example, in the Coulomb gas, I know that whatever potential you take, as long as your measure is simply connected, you always have edges which have square root, singularities. So sorry, square root vanishing. So is that true with your exponent gamma K for any potential here also?
So when you have any any potential, you have to be slightly careful, but one can work it out for other potentials. So x square is just an example. So
I'm just asking how it vanishes at the edges, because that is universal usually in the Coulomb gas.
Right. Yeah. Okay. So I need to think about it. But for example, for the k equal to 2 case, I would think that it should still go as this. So okay. So this is something which we have to work out. But if this is the external potential, I would think that for k equal to 2, this is how the density should. This is the shape the density should take. Okay.
Yeah, thank you.
Okay. But I think one should be there's a little bit one should work it out carefully. But you can set up the problem for arbitrary potential. In fact, we have some results for other external potentials. But I think it will be interesting to just confirm how it scales at the edges, right? That's your question, right? So I think we have the results, but we have not confirmed exactly how the scaling changes. Yeah. Okay. Okay. So now these densities. So how are these densities obtained, right? So what are these densities? So these densities are obtained by minimizing the action through a saddle point calculation. So what we finally can derive is some action, and then you minimize this action, and then you basically get the form of the density. So this action has basically, of course, a normalization, and there's an entropy term, and then there is this energy functional. So this is the main thing, right? So this is the energy functional, which we have managed to derive for various regimes in K. Okay, so that is the so there are two layers of complication here. One is to derive the action, and next is to do the minimization and get explicit solutions. Okay, so there are two steps that need to be done here. So this is our expression for the so by the way, I just want to say that several details are available. I have added several details, but I won't have time to discuss that here. But I'm happy to discuss it anytime after the talk also. Okay, so this is basically the answer. So the energy functional for k greater than 1 is this local theory. Okay, so I hope everyone is clear about this. And for k less than 1, it is actually a non-local theory. Okay, it's a non-local field theory. So don't worry about k equal to 1. It's there are logarithmic corrections, and it's still a local theory. But this is basically how the energy function looks. So this is how it is represented. Now let me just demonstrate it simply for the for example for Kalojra model case for k equal to 2. You notice that from here I have rho power k plus 1, which is rho cube. Then I have this piece, which is nothing but x square rho. Okay, and then I have a mu rho, right? Then I have a mu rho. So this is very hand waving this thing. But then if I minimize this, I will get something like rho square plus x square is equal to mu. And so rho is nothing but mu minus x square root. So automatically I get my Wigner semicircle very easily. In this region, it is a little more complicated, because even after minimizing, you end up with non-local equations, but you can use some techniques to find the expressions for densities. So, but the main message here is that for k greater than 1, the effective field theory is local, and for k less than 1, it is non-local. So now let me just go to finite range case. So of course, one can sort of, in some sense, generalize this model to finite range. Let's say that every particle is just coupled to d particles to the left and d particles to the right. Right? Till now, I spoke about all-to-all coupling, but here I have d particles to the left and d particles to the right. And then so there's a small modification to my energy. And why finite range models? That's because, I mean, first of all, because of screening effects in realistic systems, it is more natural, in fact, more physical to have finite range models. And there's this rho log rho term, entropy, and it just turns out that it starts becoming relevant in reasonable temperature regimes for the finite range models. So let me just go to the results here. So again, this is the external potential. This is the interaction. And what happens is that in this case, for k greater than 0, you have a support which goes as n power k by k plus 2. Okay, so it is finite support for k greater than 0. And for k less than 0, the density actually becomes Gaussian. So it really doesn't know about this interaction, because entropy dominates so much that it just becomes Gaussian. And k going to 0 is a very interesting limit. Also, okay. So the finite range case is quite different from the all-to-all coupling case. So here are some examples, somewhat related to questions that was asked. We actually considered, things like double well potential, experimentally motivated, because these are, and also box-like potentials, which are now experimentally very relevant. So cosine hyperbolic is like a reasonable box, and several interaction potentials. And basically, one can work out the density profiles, and basically these are results that just show that our expressions for the analytical expressions match perfectly with some Monte Carlo numerics. So all I'm trying to say is that we have analytical expressions for density, and those analytical expressions match perfectly with if you just do a direct numerical simulation using Monte Carlo, and then numerically compute the densities. So one more important thing I wanted to say here is that the densities we derive is coming after doing minimization of the action. But to actually derive the field theory, one has to do a very systematic derivation. If you naively try to write a field theory, you are bound to fail in many of the regimes. So I want to highlight that, which is anyway in summary of my first part, so to say, that okay, so let me just summarize first. So when you have a long range all-to-all coupling, there's a local field theory for k greater than 1, and there's a non-local field theory. And to derive this, one has to do it very systematically, because if you try to write down some effective collective description naively, you are going to get wrong answers. You might still get some dome coincidentally, but you will definitely get, it will many times just be wrong compared to what is actually the case. And for finite range, it turns out that for all k, the field theory is local. By finite range, I mean that the range is order 1. Of course, if the range itself starts scaling with n, then it's a very complicated problem. And in finite range, what happens is that there's a regime where interaction dominates, and then there's a regime where entropy dominates, and then there's k going to 0, where you have both dominating. Okay, so now I'll discuss what happens if you add a wall. So once you imagine you have this gas, and you slowly bring a barrier. Okay, so obviously if the wall is too far to the right or too far to the left, the cloud doesn't care. But what happens if you bring it where you start smashing the cloud? And the question is, how does these densities rearrange themselves, right? So that is also a very complicated question, and we tried to answer this question mainly because it is one of the starting points to compute extreme value statistics, but also this is experimentally feasible and an interesting question to ask. So recap that this was the density profiles without the wall, or if the wall is very far. Okay, so recap that this was the density profile. So this is this thing. These blue vertical lines are just trying to show that these are all having finite support. Okay. Okay, so now let me bring the wall. So let me take a wall and just bring it like this. Okay. So these are our results. So let me show the results in some order. So let me start with large K. Okay. So when you have large K, what happens is that this wall essentially pushes the particles, and the dome gets just cut. So you just have like a truncated dome. So the density profile just looks like this. Okay. So what happens is that at the wall you have some finite density, and then you get and then you have finite support on the other side. So you have a broken dome. And so truncated dome and finite support on the left. So by finite support, I mean the densities are just going to zero on the left. Now there is this regime where the wall is coming, and then at the wall, actually particles accumulate, and you have an integrable divergence, and then a finite support on the left. So the particles are sort of getting stuck to the wall, and they're basically forming some, not stuck, they're basically accumulating near the wall, and then you have an integrable divergence, and then you have this kind of shape. So the next regime is perhaps the most exotic. This is when K is between -2 and -1. So notice what happens is, okay, so this is the wall. What happens is that the wall, when you start bringing the wall, some amount of particles get stuck to the wall, and then there is a hole that is formed in between, and then there is the remaining density arranging itself like this. So you have basically two disjoint pieces. Okay, so you have two disjoint pieces separated by a hole, and some particles are stuck to the wall. Then there's a hole, and then there's another density profile that goes like this, and it develops an integrable divergence on the other side. So this is a very fascinating density profile that is sort of not at all, I mean, very hard to expect this, and this is basically what I wanted to show.
Just a simple question. So on this wall, is a finite fraction of particles is really on this wall, or just somehow?
Absolutely. So in this wall, there's actually a finite fraction of particles. So this wall, the density on this wall can be thought of something like d delta w minus x.
Okay, thank you.
In fact, I have the form in the next slide. Yeah. So in fact, very related to the question, indeed, so this is, I'm just focusing on this exotic case. So indeed, what happens is that suppose the wall is at some position, then this is what I was trying to show, that there's a finite delta piece, and then there is this extended piece. This is the extended piece, and then there is this finite fraction which is stuck to the wall. But then what happens in the system is that if I start pushing the wall more and more below some critical position of the wall, then everything gets absorbed to the wall. Okay, so there is a critical wall position, so I am bringing the wall, and then after some critical position, all particles get stuck to the wall, and there is no more extended piece. This entire extended piece basically vanishes away because all particles get stuck to the wall. So the d delta omega minus x, which I was mentioning, this d will almost become close to 1. It will just become 1 at w going to w critical. Okay, so this is so till now I discussed results about collective densities, under various conditions and so on, where we are mainly interested in density of the cloud, and we sort of forgot about microscopic particles. But we would like to go back to this question about what are the interesting things about just some microscopic quantities. And this is also important question, because there are many experiments now where one can resolve particles at the level of single atom. One can resolve at the level of single atom, so you can really in principle probe like H particle, motion of the H particle, fluctuations of the H particle, and so on. So here I'm just going to show just few results here. So we are going to stick to bulk. So by bulk, I mean that this I is basically far from 1 and far from n, and interparticle separation is basically this. So this is the interparticle separation between two adjacent particles in the bulk. Okay. In fact, I'm going to focus on delta n by 2. N by 2 is literally the one in the middle of the cloud, right? So it turns out that the mean of the interparticle separation has a power law dependence in number of particles, which is given by ak, n power minus ak. And then there are these gap fluctuations, which also have a power law behavior with system size. So these are results and from Monte Carlo simulations, where we can compute the mean and gap fluctuations as a function of system size, and this is how they behave. Of course, this mean is something that we can derive. We can write down based on our expressions for density, because density in the middle is essentially inverse of the average gap in the middle, right? So from here we can just derive these things. This is not a problem. So we see that this ak as a function of k actually is shown here. Okay. And for the gap fluctuations, we make a conjecture, and this is our conjecture, and our numerics supports this conjecture. So basically, we understand, we sort of know what the gap fluctuations in this Rees gas in this family of power law models is, and there are also supporting arguments from some small oscillation theory and some quadratic field theory and so on. So the main statement is that both mean and gap fluctuations are understood in this family of models. Okay, so that is what I wanted to show. And of course, we also I did not show here. We also study the gap distribution. The gap distribution is essentially analog of what they call level spacing statistics. So here, the gap, what is the gap distribution of particles, and so on and so forth. And we have some results for various regimes in K. Okay, so next I want to talk about time dynamics. So these are very preliminary results. So let me just so till now. So what do we have till now, right? So till now, what we have is we have some field theory. So we have basically the energy as a function of densities. Okay, we have energy as a function of densities for different regimes in K, right? But now if I also add some kinetic term, like half rho v square, okay, and I call this the Hamiltonian, okay. So I can in principle study some time dynamics, and I assume that there is some Poisson brackets between rho and v, and then I can study some continuity and Euler equations and so on. So once you have a field theory, you can study collective dynamics of these fields. So, but before that, let us forget about fields. Let's look at microscopic approach to dynamics. So there you basically specify some initial conditions, xi of 0 and pi of 0, and then you basically solve these Newton equations. So this is the Newton equations corresponding to our Hamiltonian, which is basically summation I pi square by 2m plus whatever I called E of xi in microscopic variables. Okay. So, and I can give several initial conditions. For example, now that I know how these particles are arranged in equilibrium, I can make initial conditions as if you have this some initial conditions like a bump on top of this dome, like for example, right? So these are the kind of we know that for k equal to 2, the particles arrange themselves on zeros of Hermite polynomial. But what happens if I suddenly jam these particles a little bit and then just release them? Or you can study some blast-like situations where you just jam all these particles at the center of the trap and then suddenly release them and so on. So, but that involves just solving these highly non-local equations. So you have a lot of equations to you have to solve these long-ranged ODEs, and then from here, what you can do is you can just build densities. This is just for plotting purposes. So this is basically 1 over interparticle distance, and you can just calculate what is the effective density look like. So this is I just call it micro because this is not to be confused with the actual density field. This is just I have some large number of particles and I call 1 over interparticle distance as density, and I just plot it. Okay. So and then you can plot this density and even velocity data for various time snapshots. So above definition should be understood as reconstructed density for plotting purposes and should not be confused with macroscopic density field. So this is just microscopic dynamics. So one can do numerics for very, very long terms with no issues, and such as developing gradient catastrophes and such things. So you can just do this microscopic dynamics which are just stable. Okay, so this is one thing, and also for this kind of models we studied some classical version of out of time ordered correlators recently. So this is just the microscopic story. Now let us go to the field theory approach. So the field theory approach would be you specify initial conditions of density and velocity fields, and then using Hamiltonian and Poisson brackets, you actually write down some continuity and Euler equations. And this is the exact expression in large N. So this is the expression in large N, where you see that you have this v square by 2, and then this is the trap, and this is W of rho, which for k greater than 1 it is local, and for k less than 1 it is non-local. Okay, so this is so for k less than 1 it's a non-local partial differential equation, and for k greater than 1 it's a local partial differential equation. In fact, just as a remark, very quickly you can see that for the Kalozha model, you will quickly see that you get the semicircle right away. So what is the equilibrium density profile, right? When velocity is 0 and when this piece W square y square by 2 plus okay, don't get confused with this W of rho is equal to some constant. But this W of rho is nothing but, for the Kalozha case, it is just rho square. Okay, so you will get y square plus rho square is equal to constant, which implies rho is constant minus y square root. So you can get all sorts of density profiles just by looking at equilibrium solutions to this equation. But anyway, that is not my main point. So my main point is that you can take these and now you can plot this for various time snapshots. Okay, so of course this is just a large N theory. These equations are expected to yield some catastrophes at large time. So what happens is that if you start with some initial condition, presumably what happens is that after some time these profiles develop sharp gradients. They become very steep, and there are no terms in this equation that can correct for those steepnesses. So you may run into some catastrophes, but till that happens, you have good dynamics. Okay, so this is so now I'll show you some results, and I hopefully it will become more clear what I'm talking about. So let us focus only on one side first. So this is k equal to 4. Okay, this is k equal to 4. So here what we are here we are plotting. So our initial condition for this. So for k equal to 4, the density profile, background density profile will look like this, right? It's a dome. Okay, but our initial condition is like this, something like this. So it's like a bump on top of a dome. Okay, so the particles are arranged such that they form a bump on top of this dome, and say initial velocity is 0, and then you let it evolve. So at t equal to 0, and just for plotting purposes, we subtract off the background. So at t equal to 0, you see that this is the profile. And slowly as time evolves, you see that this profile is splitting and doing all sorts of things. And this dotted things here are microscopic data from solving this. And these solid lines are basically these partial differential equations. Okay, so there is remarkable agreement between both. So basically, solving microscopically solving these dynamics for, let's say, 512 particles, one can reduce it to solving just like a local partial differential equation for k greater than 1 case.
And do you sort of form shock waves on the left and right?
Okay, so that's a very, very interesting question. So indeed, what happens is that you see at t equal to 0.4, what happens is that it appears that the profiles steepen, and it seems like you are sort of running into some shock. But presumably, so of course this is the partial differential. This is the field theory, but microscopics, you can run it for longer times, and microscopic will keep evolving. And the question is, what are the corrections to this piece? So what are the corrections to this piece that could correct these shocks? So let me just make it more specific. So for k equal to 4, which was my plot, W of rho was rho power 4, right? So what I have is, so I have rho power 4. But imagine in addition to this, I have dy rho. Okay, so second derivative of rho. And then there's one more extra derivative here, which will be third derivative, 3 derivatives of rho. So this kind of triple derivative terms, etc., could start giving oscillations. And so we can call them dispersive shock waves. So at this moment, we are still probing this. So it's not clear what is happening here. But certainly, if you stop with this, oil is run into shock. Yeah.
So supposedly you have diffusion terms as well, not purely dispersive.
That can happen as well. So indeed. So okay. So I that was an example. So you can have basically two type of terms to correct it, right? One is dispersive, and one is some effective dissipative, right? Effective dissipative. In effective dissipative, what would happen is that this shock would sort of just this slope would be slightly made a little bit this thing, and it will just evolve like this. Okay, so so it won't produce oscillations. But to know what is the effective term that is relevant, that's what we are trying to probe. And from microscopics, our hope is that we will get some intuition about what is the effective term which is.
So you don't have noise in your equations, right?
No, we don't have noise. We don't have noise.
Working at zero temperature, is that the thing?
Yes. So at this moment, we are talking about zero temperature and initial value problem. Yeah.
Okay, because if you work at finite temperature and you work in the overdamped limit, then there is a formalism due to David Dean, which will allow you to get the continuum equations for the evolution of the density and so on. So if you have noise, then there's already a formalism which will allow you to get the evolution of the density in the overdamped limit.
Right. Yeah. So that would be, so what would be interesting is to find out those effective terms, and then to add to sort of along with the information that we have this term, right? So the thing is, this term we have derived it very systematically, and question is what are the next relevant terms? So yeah, one could try to see how to combine all these things together and get some regularized dynamics. Yeah. But I just want to say that there are in principle more terms here, okay, but it's very hard to keep deriving them. But then the idea is forget this and just do the microscopic dynamics. From there you should get an idea of what is going to happen here for the microscopic dynamics, and then from there you can write down what is the effective term in the partial differential equation which can mimic that. So for example, suppose I do the microscopic dynamics, Newton's equations, and I realize that after this there is no oscillations, it is just this front is just moving, right? Then I know that it is presumably the effective theory has a small dissipation piece which is correcting this shock wave, okay? But on the other hand, suppose the microscopic dynamics show that after this there are some huge oscillations. Then I know that presumably the next relevant term is going to be this kind of dispersive correction, okay? Triple derivative of y, rho. So there's a lot of things here, but at least it is very nice that to the times where the partial differential equation makes sense, it agrees remarkably well with the microscopic dynamics. And for k equal to minus 0.5, so this is local PD, and this is for k equal to minus 0.5. So that is actually a non-local partial differential equation that we have to solve. And then there you can see that you have some, this is the initial condition, and there is some evolution. And here somehow it doesn't seem to run into, so it seems to work pretty well, but we still have to go longer in time and analyze this properly. But till the times that that I'm showing here, there's very, very good agreement. Okay. Notice that they're very different. There's a lot of difference between these two because here the peak is splitting, and here the behavior is slightly different in this case. But I just want to show that there's a non-local dynamics and there's a local dynamics, both which agree with their respective microscopic starting points. So here for k going to greater than 1, the field theory seems to certainly predict onset of shocks, and which are expected to get regularized by higher derivative terms. And we know this story reasonably well for k equal to 2 So it's not very surprising, but what is unclear is what is really happening. That is not clear, and there are very fascinating open questions on thermalization. And so there are some videos of this microscopic evolution, which I can probably maybe just show here actually. So okay, you can see the screen, right? So this is basically k equal to 2 case. So k equal to 2. So this is some initial condition, and you see what happens for k equal to 2 is that it just keeps on evolving. Okay, this is just pure microscopic dynamics. Okay, this is just pure microscopic dynamics, not any partial differential equation. And this is understandable because k equal to 2 is integrable. So this thing just doesn't thermalize at all. And in fact, k equal to 2 is very special, that the dynamics repeats itself after 2 pi by omega and so on. But this is k equal to 2 case. And this is I think k equal to minus 0.5. You see what happens is that eventually at long times, it seems that somehow the effective dynamics is sort of resting on this dome. So this yellow line you see is just the dome, and it seems that the system shows hints that in the long time limit, it will just keep thermalizing to some dome whose formulas and whose expressions we know. But okay, these are very preliminary results, so I wouldn't worry too much about them at this moment. But yeah. So that is the thing. And in conclusion, so we have collective description and statistical properties of long-range systems. There's a big difference between all-to-all coupling and finite range models. So maybe I rest through this a bit too much, but I just want to say that finite range models have situations where the density may not even have a finite support. So you can have Gaussian density profiles and so on. So, and entropy, we can see how important entropy becomes in these finite range models. We showed results in presence of a barrier where very non-trivial things are happening. There is exact agreement between Monte Carlo simulations and our analytical results. We studied some bulk gap properties and some initial value problems in time dynamics. So we are studying extreme value statistics, and we are also interested in emptiness formation probability, number variance, and correlations in this family of models. So when I say finite range models, I mean that D is basically order 1. And if D is n or n minus 1, then it is all-to-all coupling. So how it interpolates between this is a very interesting question. And what happens between low and high temperature crossover, that is also very interesting. And I mean, this is something which we are just thinking about. It is quite unclear, but it's interesting to probe thermalization, mainly because we know that W of rho in the Euler equation. So the point is, the fact that we know this, we want to exploit it to do further studies. And there are efforts in experiments where they are planning to scale up these long-range systems, especially in experiments involving K close to 1 in ions, which also I am sort of trying to understand. And these are some of the references. And thank you for your attention.
Thanks, Manus, for a really beautiful talk. If there are questions, please raise your hands or just unmute and ask. Yeah, I think you clicked at the same time, but maybe Tomohiro.
Okay, sorry, Benjamin. Thank you. Yeah, so in the first part of your talk, you mainly discussed the density profile, right?
Yes.
And so to get that analytically, you are using kind of field theory. So I think this is, so in the language of random matrix theory, this is basically equivalent to something called Coulomb gas method. Is it correct?
Yes. I mean, for the log gas, you can write a field theory, and we are essentially generalizing that to arbitrary K.
Gap and yeah, maybe it's basically gap.
Yeah, the mean and the variance. Yeah.
In the case of random matrix theory, of course, one can get, you use orthogonal polynomial method and so on to calculate correlations and gap probabilities. But in this case, how can you study these quantities?
So sorry, I think first part of your question I sort of did not hear. What did you say?
How can you study these quantities? Gap, for example, gap probability.
Okay. So at this moment, all these results are essentially numerical. And in fact, the gap statistics, let's call it P of S, also is entirely numerical. And in fact, there is very little analytical understanding of this gap statistics. Yeah. So that's a very hard question. In fact, only one specific case of K going to 0, which is the log gas. Here, of course, we get Wigner's surmise and those kind of things, but everything else is numerical. Yeah.
Paul, did you have a question?
I'm not sure I remember 100%, but I think that very famous and like classical hydrodynamic would be, of course, without omega, but W would be like rho cube. It corresponds to shallow water approximation or something like that. And that shallow water, some maybe little generalization, also known to be like integrable appear close to solitons or whichever. So anyway, sort of wonder if it's correct, maybe you should look more carefully at k equals 3, which you told us it's what it is, I forgot.
Oh, I see. Okay. So you're saying the k equal to 3 case, so W will be rho cube, right?
Yes, and it's kind of really very often appears in somehow incompressible in description of shallow water. Rho would be actually there in shallow water would be the width of your like of this water, but it's actually mathematically it's identical, and it's very was popular maybe 100 years ago in like. But it has really somewhat remarkable, like special value, somewhat remarkable, as far as I vaguely recall. Equations, yeah, and there was some generalization, forgot the names, which was sort of popular in terms of when it was like solitons. Anyways, so it may be, it's kind of interesting also a number for you to maybe to look more carefully. I doubt you would have such outstanding results like in Focaloger, where it's really this revival going back and forth. Yeah, whichever it is, yeah, but maybe.
W equal to, I just wanted to make a comment that the k equal to 2 case without the trap would be something like y square by 2 plus rho square. So this basically can map to something called Riemann-Hopf equation. And so those are and those terms of Riemann-Hopf are part of KdV equation, but I was not but this is not k equal, this is only k equal to 2. So it's interesting to see if k equal to 3 has some equation which has soliton. You're saying there's a chance that there are solitons.
It's not exactly solitons, but some generalization of that k equals 3.
Oh, okay.
I vaguely recall, so somehow it's not far away. And somehow it's outstanding also example considered. And also you can connect to all the literature,
Okay.
So, but definitely nothing was done with this y squared over 2 term. It was, in hydrodynamics, there is no such external potential.
Okay, yeah. Okay. Thanks, yeah.
Dave, you had a question?
Hi, thanks for the talk. Just to clarify the collective field theory, it's an exact rewriting of the microscopic dynamics, right? And then you're expanding in large N, so there's not really a fluid assumption or a thermal assumption. Is that correct?
Yeah, so it is a rewriting of microscopic variables in terms of density fields and then expanding in terms of large N. So that statement is correct. So it is a systematic expansion in large N, starting from microscopics and going to a field.
Yeah, good.
So yeah.
So you're not coarse graining or taking any temperature average.
Okay. Can I add some little bit? So I think you're not coarse graining, but you are making an approximation implicitly somehow in this calculation, because if it is integrable, for instance, these equations are kind of just incorrect and you're missing a lot of other conserved fields. And so these equations kind of come out naturally from the macroscopic dynamics. So you just write down collective variables, delta of x minus xi and things like that. And then you write down the equation of motion, you get that kind of immediately, but this is not entirely correct. There's some approximation being made there to see that this is the only equation that are relevant. And it's not completely clear where the approximation is, but
for the Calorimeter model, if you just take this piece, if you stop here, then it's not integrable. The PD is not integrable.
Yeah.
You have to write the dispersive terms, etc., and then it'll be a non-local PD, and that is integrable. But if you just stop the thing at large N, then you break integrability.
Yeah, no, I understand. But what I'm saying is that if the macroscopic model is integrable, then you wouldn't expect just these equations to be the correct ones.
Absolutely.
For describing the Laurent dynamics.
Absolutely. So if the microscopic model is integrable, then it's probably not good to stop here.
Yeah.
But it depends on what you're interested in the sense that, of course, you will not get the kind of the dynamics that I was showing you for Kalojra, which was this back and forth this thing. If you just evolve it like this, you will run into problems, right?
Yeah.
But it depends on what you're interested in. But for a large set of questions, we can stop here and analyze.
So I'm not too sure. Maybe I'm confused about it. Sorry, I'm taking a bit of time for my question. But so if we do the derivation kind of collective modes, we get these equations. If the microscopic equation is integrable, I would expect the hydrodynamics to have many more equations, not just higher order term, but just more collective fields. However, we know that at zero temperature, so this GHD at zero temperature actually comes back to these equations only. So is it that you can stop here because you are at zero temperature or at very low temperature?
Okay, so I think even at zero temperature, you will have these two equations, but technically you will have more terms in this W of rho, right? So W of rho you cannot stop here.
Like higher order terms, right?
Higher order terms, yeah.
But so this we keep say the trap is kind of large scale enough, and then we can neglect these. That I think we can control these terms. Higher order terms, I mean derivative, higher order term derivative. We can control these terms.
You can control, but the point is it depends on what you're interested in. For example, if you want to derive soliton solutions for the Kalojra model, these higher order terms are very important to actually get the true soliton solution. So it again is what you're looking for, I think.
Yeah, so if you keep the third order term, there's a whole integrable hierarchy, isn't there?
Yeah.
Sorry, what do you say?
If you keep the third order term, isn't there a whole integrable hierarchy of commuting flows for this?
Yeah. So there's a that's right. There's a third order term. Yeah, and then you can show and indeed if you write the third order term and probably few more terms, you can show that this model has multi-soliton solutions and so on, which is basically strongly indicated that it has that it is likely to be integrable. So sorry, are you able to hear me?
So maybe Manas, maybe we can continue this in the breakout room, the discussion.
Sure. Yeah.
Right, yeah. So I think we have run out of time. So thanks again, Manas, for the really great talk. And we'll have a break now for an hour. But there are the breakout rooms, and so Vincenzo will go to the breakout room 1, and Manas to breakout room 2. And anyone who's interested can join them.